After completing Chapter 4 on relative humidity, we did a few problems in class, and there was a request for a video to be produced to go through these problems again for later review. So we'll start off with question 1 that we went through in class. In this question, they gave you the temperature and the dew point for 3 cities in the United States. The question asks you to use Table 1 of Chapter 4 in your book to calculate the relative humidity for each of these cities. The formula that we'll use in this problem is going to be that the relative humidity equals the E over E sub S, which is the vapor pressure divided by the saturation vapor pressure, times 100. The E, or the vapor pressure, will correspond to a reading on our chart to the dew point temperature that was measured, and the E sub S, or the saturation vapor pressure, will correspond on our table to the temperature that was recorded. This is an image of Table 1 on page 102 in your textbook. The table is divided in 2 sets of 3 columns each. The far left column is the temperature recorded in degrees Celsius. The middle column is the temperature recorded, or the dew point, in degrees Fahrenheit. And the third column is the vapor pressure, or saturation vapor pressure, measured in degrees millibars. If we go back to our problem, we see that for Atlanta, Georgia, the temperature was recorded at 90 degrees and the dew point was recorded at 75 degrees. If we go back to Table 1 on page 102, we correlate the temperature of 90 degrees to a vapor pressure, or saturation vapor pressure, to 48.1 millibars. We correlate the dew point temperature of 75 degrees Fahrenheit to 29.6 millibars. So to set the problem up, we first take a look at the temperature of 90 degrees Fahrenheit, and we correlate that to our saturation vapor pressure of 48.1 millibars from Table 1. We take the dew point temperature of 75 degrees Fahrenheit, and it's correlated to the vapor pressure as taken from Table 1, measuring 29.6 millibars. We insert these values into the formula for relative humidity, and we see that the relative humidity equals 29.6 millibars divided by 48.1 millibars times 100. That equates to 61.5%, or rounded up to 62% relative humidity. Looking at Baltimore, Maryland, where the temperature is 80 degrees Fahrenheit and the dew point is 70 degrees Fahrenheit, we once again go back to Table 1 on page 102. We correlate that 80 degree temperature to 35 millibars of saturation vapor pressure and a 70 degree dew point to a 25 millibar vapor pressure. Putting this back into our problem, once again the temperature of 80 correlated to a saturation vapor pressure of 35 millibars as taken from Table 1. A dew point temperature of 70 degrees Fahrenheit correlated to the vapor pressure of 25 millibars from Table 1. We insert that into our relative humidity formula, and we see that the relative humidity equals 25 millibars divided by 35 millibars times 100. That equals 71.4%, or rounded to 71% relative humidity. Finally, for Norman, Oklahoma, the temperature is 70 degrees Fahrenheit and the dew point is 65 degrees Fahrenheit. Going back to Table 1 on page 102, we correlate that temperature of 70 degrees Fahrenheit to equal a saturation vapor pressure of 25 millibars, and a dew point temperature of 65 degrees Fahrenheit is correlated to a vapor pressure of 21 millibars. Solving the problem once again, temperature of 80 degrees Fahrenheit correlated to the saturation vapor pressure of 25 millibars from Table 1. Dew point temperature of 70 degrees Fahrenheit correlated to a vapor pressure of 21 millibars from Table 1. Insert that into the relative humidity formula. We see that the relative humidity equals 21 millibars divided by 25 millibars times 100 equates to an even 84% relative humidity. Those are the 3 answers for question 1. In question 2, we took the temperature, dew point, and relative humidity, and we look at the 3 cities during a July afternoon. Using both the relative humidity and the air temperature, we want to determine the heat index for each city. In order to determine the heat index for any point, we're going to use a heat index chart. For this problem, we're going to look at figure 4.19 on page 104. The chart is laid out very simply. Across the top, you have the relative humidity axis. Across the left side, you have the air temperature axis in degrees Fahrenheit. If your problem had given you your air temperature in degrees Celsius, you would have had to convert it first before applying it to this chart. So going back to our problem and looking at Atlanta, Georgia, we see that the temperature is 90 degrees Fahrenheit. The relative humidity is 60%. We go back to figure 4.19 of our textbook on page 104. We find 90 degrees Fahrenheit on the left axis. We find 60% relative humidity across the top axis. We draw a line over from the temperature and a line down from the relative humidity, and where the two intersect is where we read our heat index. In this particular case, the heat index is 100 degrees Fahrenheit. When we look forward to Baltimore and Norman, we go back to our heat index chart for figure 4.19, page 104. Apply the air temperature and relative humidity. You should be able to compute a heat index of 85 degrees Fahrenheit for Baltimore and a heat index of 71 degrees Fahrenheit for Norman, Oklahoma. In the next problem, each individual teams measures the following temperatures and dew points in 3 locations. You're asked to calculate the relative humidity using table 1 on page 102. This is the same process we did in problem 1. You should compute a relative humidity of team 1 of 53%, team 2 51%, and team 3 61%. Now a question asks you, what does the dew point temperature tell us about the water vapor content in the air? According to your textbook on page 98, the dew point is a good indicator of the air's actual water vapor content. As the dew point goes up, the water vapor content increases in the air. As the dew point goes down, the water vapor content decreases. Note that as the water vapor content or the dew point changes, the relative humidity changes as well, but it doesn't necessarily correspond to the highest amount. In this case, the highest relative humidity was 63% on team 3, but it did not have the highest dew point temperature. So the next question was, which location has the highest amount of water vapor in the air? And we're going to indicate that that's team 1 with the 75 degree Fahrenheit dew point temperature. Now note in table 1 that the relative humidity is in 5 degree Fahrenheit increments. If we read the problem using relative humidity, you calculated in the temperature what is the heat index. The table for heat index doesn't have individual degrees, so we're going to interpolate across that chart. Let's go back. This is figure 4.19 on page 104. Find the air temperature of 95 degrees. And the relative humidity was 53%. It's somewhere between these two columns indicated across the top. As we indicated in our previous procedure, we draw a line over from our air temperature, and we come down from the top axis between the 50 and 55% relative humidity lines, and we see that our heat index is somewhere between 107 and 110 degrees Fahrenheit. We'll average those two values out simply by adding 107 degrees plus 110 and divided by 2. And it equates to 108.5 degrees, or rounded up to 109 degrees Fahrenheit heat index. You'll do the same process for team 2 and team 3 with the temperature and relative humidity values that are there. When you do that, you should compute an 81 degree Fahrenheit heat index for team 2 and a 95 degree Fahrenheit heat index for team 3. The next problem looked at the wet bulb, dry bulb temperatures for 3 teams once again. Your teams were measuring the following air temperatures and wet bulb temperatures using a sling psychrometer. In Team 1's case, you had a 35 degrees Celsius dry bulb temperature with a 30 degrees Celsius wet bulb temperature. Team 2 is 35 and 28.5 on the wet bulb and temperature. And Team 3 had a 30 degrees Celsius temperature with a wet bulb temperature of 20 degrees Celsius. You're going to use Appendix D in your textbook to calculate the following questions. First of all, what is the wet bulb depression? The wet bulb depression is simply defined as the difference between the temperature and the wet bulb temperature. So in the case of Team 1, the wet bulb depression is 5 degrees Celsius, and we obtain that by subtracting 30 degrees Celsius from 35 degrees Celsius. In Team 2, the wet bulb depression is 6.5 degrees Celsius, which is obtained by subtracting 28.5 degrees Celsius from 35 degrees Celsius. And then Team 3, the wet bulb depression was 10 degrees Celsius, and that was obtained by subtracting 20 degrees Celsius from 30 degrees Celsius. The second question that's asked is to compute the dew point temperature using table D.1 in the back of your textbook. This is an image of table D.1. On the left axis of the chart, we see that that's the air temperature, or what was recorded on the dry bulb, and note that those are in 0.5 degree Celsius increments. Across the top of this chart, we have the wet bulb depression in degrees Celsius once again, in 0.5 degree increments. In the first problem that we had, we recorded an air temperature of 35 degrees Celsius and a wet bulb depression temperature of 5 degrees Celsius. Like we've used in other charts, we draw a line over from the left off the air temperature and down from the wet bulb depression, and we see that the dew point temperature is computed at 28 degrees Celsius. You'll do the same process for Team 2 and Team 3. When you do this, you should come up with a Team 2 dew point of 26 degrees Celsius and Team 3 dew point of 14 degrees Celsius. Now that you have the temperature and the dew point, you can go back and you can use table D.2 to determine the relative humidity. This is just another chart, another way of computing relative humidity. If we look at table D.2, on the left side of the graph, we have once again the air temperature in degrees Celsius. Across the top, we have the wet bulb depression. And just like we did in the previous problems, we're going to find our temperature on the left side, which was 35 degrees. Across the top, once again, we have our wet bulb depression of 5 degrees Celsius. We draw our line over from the left, and we come down from the top axis. We see that our relative humidity is 69%. Now, in previous problems, we used table 1 on page 102. Let's compare how we compute relative humidity using this chart from the answer we get from the other chart. We're going to carry over and find that the saturation vapor pressure when the temperature is 35 degrees Celsius equals 56.2 millibars. The dew point temperature was computed at 28 degrees Celsius. Now that's between two values here on our chart. So what we're going to do is we're going to average out the vapor pressure here by adding 35 plus 41 and divided by 2, and we see that when the temperature on this chart is 28 degrees Celsius, the vapor pressure is 38 millibars. We put that into our original formula that we were using earlier on, and we see that with table 1 on page 102 we compute a relative humidity of 68%. That 1% difference between the two charts is mainly due to rounding errors in our values. It's statistically insignificant. If you can be within plus or minus 5% of your relative humidity, you probably got a good calculation. If you go through Team 1, 2, and 3, the 3 relative humidities listed here should be the answers you get using table D.2. That concludes this exercise of reviewing those problems we did in class. If you have any questions, please feel free to send me an email or give me a call, and I'll walk you through those problems again. Thank you.